Double replacement reactions. What I saw so far is that some people might need a little more practice with balancing reactions, balancing equations, and getting a little bit more practice on working and understanding what a net ionic equation is. So this video is dedicated to double replacement reactions. Now, what you need to remember, above all else, is that these are not redox reactions. There's been some confusion. Single replacement reactions are almost all redox reactions. Double replacement reactions primarily follow solubility rules, or basically what you have is you will have different ions coming together and forming new products. Let's take a look at this a little bit more closely. Here I have phosphoric acid, or hydrogen phosphate, but when it dissolves in water, it's phosphoric acid. Sodium hydroxide, which also dissolves in water. Now, again, according to solubility rules, most hydroxides are insoluble in water, except solubility tables will tell you that group 1 or group 1A, which are the same groups on the periodic table, group 1 elements have soluble hydroxides. Now, another way to look at acids is basically they are ionic compounds with a hydrogen ion in place of a metal, which you would typically see. And if you check the periodic table, hydrogen is in group 1, along with all of the other lithium, sodium, potassium, rubidium, cesium. So it behaves chemically very similar to sodium, for example. That's why most of these hydrogen compounds are soluble in water, and they also happen to be acids because once you get that H plus ion, which you see here, the H plus ion is what makes something an acid. Now, H plus, I have 3 of them because that's what my subscript here means. Those 3 hydrogen ions are needed to balance the phosphate, which is a -3. This is a stable compound. No net ionic, or no net charge on it, which means it's not an ion. This is an actual perfectly legitimate compound. Now, if I look at sodium hydroxide, I also have sodium ion and hydroxide ion. This is what happens to ionic compounds when they dissolve in water. Now, it's a question: is hydrogen phosphate truly an ionic compound? Well, it is, because it is a substance that dissociates, becomes ions in water, but at the same time, it is something of a molecule, because this is actually 3 hydrogens bonded to a phosphate. You would actually see that as a molecule. Acids kind of span the gap between the true molecular compounds and the true ionic compounds, which is why they're so special and why we'll have a whole unit focused on acids coming up fairly soon. Then we have sodium hydroxide. Now, in every case, and this is something that was a little shocking to see on the test, or on the quiz, hydrogen ions and hydroxide ions will come together to form water. There's no other combination between hydrogen and hydroxide that would make anything besides water. And therefore, I need to keep that in mind when I'm writing my equation. When people are predicting products, I saw H3OH, and I really don't know what that is. It doesn't exist in reality. And I saw some people putting HOH and not realizing that that's exactly the same thing as water. Yes, hydrogen ions come together with hydroxide ions to make water. That is neutralization. That's something that's going to be very important to understand very soon. So this is my molecule now. Hydrogen ion has come together with hydroxide. It is no longer an ionic compound. Now it's a perfectly legitimate polar covalent molecule, H2O. And the sodium phosphate, again, compounds for most group 1 elements are soluble in water. My apologies. So in this case, my sodium phosphate still contains, or would have to contain 3 sodium ions for every phosphate ion in the solution. Now, if I look right now, I can tell my equation is not balanced. what I also want you to see is, because these double replacement reactions are not redox reactions, just a brief overview of oxidation numbers. We've seen previously that except in compounds that include fluorine, oxygen is always a -2. Peroxide is another exception to that, but in most cases, oxide is a -2. Hydrogen or oxygen's oxidation number when it's in a compound is -2. Hydrogen is a +1. Therefore, -2 + 1, my overall charge on this polyatomic anion is a -1. If we look at water, water is still, the oxygen is still a -2, hydrogen is still a +1, and I have two of them. Now I have a balanced, stable molecule. But if you just pay close attention here, hydrogen starts as +1, +1, oxygen starts as -2, oxygen remains -2, hydrogen stays +1. If I wanted to look at the sodium, sodium is also +1. If I wanted to take a closer look at phosphate, the oxygens combined would be a -8. Therefore, the phosphorus has a +5. If you remember really closely, phosphate has 5 valence electrons. Oxygen grabs them. That's why we have this, and then it takes on three other electrons in order to make that a stable form of a covalent polyatomic anion. But that's not the important thing right now. What's important to see is that I have 3 sodiums here. They have to come from this side. I have 3 hydrogens that need to become waters, and I only have one hydroxide to do that. The balanced equation must show that all of my reactants are turned into products. I can't have leftovers. This is not limiting reactants, which we will cover a little more closely in another video. This is what I need is a balanced equation to show me that what I have in reactants is going to turn into products. In this particular case, I'll move it down a bit, I'm going to need 3 hydroxides to balance my 3 hydrogens to form waters. And it's not just going to be one water. Since I have 3 hydroxides, each of these hydroxides came from sodium hydroxide, so I need 3 sodiums and 3 hydroxides for 3 formula units of sodium hydroxide. I'm going to make 3 waters. Each hydrogen ion is going to find a hydroxide and make a water. The point of a net ionic equation is then to focus on the molecule or the insoluble ionic compound that forms. So that's what we really truly want to see. Did the phosphate change? No. I only need 1 phosphate on the right, I only need 1 phosphate on the left, and I have them. Did the sodiums change? No. And you'll note here, thankfully, since I have 3 sodiums from the hydroxides, those 3 sodiums can now, if I were to evaporate my water from the aqueous solution, these 3 sodiums would join together with phosphate and form sodium phosphate. And that is the formula unit where I have 3 sodium ions for every phosphate ion that would be in my compound. But the thing that actually changes here, I have hydrogen ion finding hydroxide and becoming water. That is going to be the focus of my net ionic equation. Sodium stays the same on both sides. This sodium in aqueous solution is the same as this sodium in aqueous solution. Phosphate is the same on both sides, both phosphates in aqueous solution. H plus has become part of water, and OH is part of H2O2. Of course, when I say H2O2, I'm reminded of this particular joke. Students have told me this several times in the context of chemistry. Of course, this H2O2 refers to hydrogen peroxide, which is definitely not something you want to be drinking. Of course, would they ever sell H2O2 hydrogen peroxide in a restaurant? I highly doubt it. But yes, you're going to be in bad shape if you drink hydrogen peroxide. So let's not try that. Now, this is what we were focusing on. I said hydrogen ions, hydroxide ions become water. That's what's important. So my 3 hydrogens come down, my hydroxides, and my water are my net ionic equation. You notice that the ratio here, 3 to 3 to 3. We want the smallest ratios in all cases. So we divide the H plus by 3, we divide the OH by 3, we divide the H2O by 3. My net ionic equation would be H plus, again, net ionic equation, H plus OH makes H2O. That's the only real change we saw in this reaction. Now, would I visibly see water molecules forming? No. But we have several different lines of evidence for a chemical reaction. We have the possibility of precipitate, which you wouldn't see here. We have the possibility of a gas forming. Also wouldn't see that here. But we do have the possibility also of temperature change. And in this case, this solution would heat up as the water is being made. So we would still see evidence of a chemical reaction. And we got it. And that didn't animate like I hoped. But anyway, we got there. That's our net ionic equation. H plus OH minus yields H2O. This is the general neutralization reaction for any acid and base reaction, which we will be seeing very soon. Just a couple of things I need to animate here. But this is another look at a different net ionic equation. In this particular case, again, we have 2 aqueous reactants. We have a precipitate, and then we have another product that remains aqueous. This, again, precipitate is a sign of a chemical reaction. Now, this one is a little bit nicer, a little bit friendlier, because, as you will see, this one is already balanced. Barium is an ion in this solution. I have 2 chlorides in this solution, BaCl2. Now, again, you need to understand, the chlorides come apart as separate chlorides that are independently moving in the solution. Same thing happens with the sodiums. I have 2 sodiums that are independently coming off of sodium carbonate. Now, solubility rules again. Most carbonates are insoluble, with the exception of the group 1 or group 1A elements. Hydrogen would be included in that group. So group 1 is how we typically refer to the periodic table now as the alkali metals. Previously to that, it was called group 1A. Group 2A were the alkaline earth metals. Group 3A was the group where aluminum is. And then we had the halogens. They were group 7A. That was reflective of the valence electrons. The transition elements were referred to as Bs instead of A's, because we had what were called the representative elements, which were all of the non-transition elements and then the transition elements. But nowadays, it's just basically 18 columns across the periodic table. But when sodium carbonate dissolves, we then get carbonate ion. Now, again, checking solubility rules, barium carbonate is a precipitate. It is a solid. When a floating around barium ion happens to find carbonate, those will come together and form barium carbonate. That's a good indication of what our net ionic equation might be. And then I have 2 sodiums. I have to move that arrow over a bit, but 2 sodiums and 2 chlorides. Now, this was another confusing thing that I saw certain students do. They saw Na2 here, they saw Cl2 here, and they wrote Na2Cl2. That is not the proper representation for an ionic compound. Ionic compounds are formula units. Formula units are the simplest whole number ratio. So if I had Na2Cl2, the simplest whole number ratio between them would be 1 to 1. It has to be NaCl. It can't be Na2Cl2. That would suggest something that just isn't there. What I have in a crystal of sodium chloride is I have 1 sodium for every chloride. Yes, I would have 2 formula units represented by this ratio, but I can't write this as Na2Cl2 or Na3Cl3. It has to be NaCl because that's the smallest ratio of one atom to another in my ionic compound. And again, to look at it a little more closely, this is what a salt crystal actually looks like. Sodium chloride crystal actually looks like. I have my sodium, I have my chloride. I have my sodium, I have my chloride. At no point are the sodiums sticking together as an Na2 might imply, or Cl2. Yeah, they touch, but I mean, they're it's just a matter of their arrangement, their crystalline arrangement. But the ratio is 1 sodium for every chloride, 1 sodium for every chloride, 1 sodium for every chloride. This would be 1 formula unit, NaCl. This would be 2 formula units, 2 NaCl, as we see right here. Okay, I have to animate where our net ionic equation is because we haven't gotten there yet. But we focus on the product that changed. Chlorides stay chlorides. Sodium ions stay sodium ions. Barium carbonate is no longer barium ions floating around with carbonate ions. This is now a precipitate, which is a good sign of a chemical reaction. So we have our barium carbonate solid. Now, for a net ionic equation, ask yourself, what did barium carbonate come from? It came from a barium ion and a carbonate ion, and that's your net ionic equation. One more, just to take a look, would be this. Silver nitrate, and again, by now we should definitely be familiar and comfortable with naming compounds. So silver nitrate, aluminum chloride, silver chloride, and aluminum nitrate. Most chlorides are soluble. Aluminum chloride is soluble. All nitrates are soluble. Aluminum nitrate is soluble. Silver chloride is one of those exceptions to chlorides being soluble. Silver chloride is a solid. It is insoluble in water. Don't confuse S with soluble. S means solid because it's insoluble in water. So all nitrates are soluble. Most chlorides are soluble, except silver chloride is one of those exceptions. Aluminum nitrate, again, all nitrates are soluble. Silver chloride is actually a very interesting compound. It's used to seed clouds. If there's an area where there isn't a lot of rainfall and you have some water-heavy clouds drifting over an area where they need the rain badly, of course you need those rain-heavy clouds. You can actually seed the clouds with finely ground silver chloride, spray it through the clouds. It will cause water to condense around the silver chloride and it will cause rain. So even though silver chloride is not a soluble compound, it does interact with water and can make rain in a place where you might desperately need it. But again, to look at our formula, this is not balanced. And how do I know it's not balanced? I have 1 silver ion. I have 1 nitrate polyatomic anion. I have 1 aluminum ion. I have 3 chloride ions. I can already see a problem because chloride has a -1 charge. Silver has a +1 charge. Silver chloride is balanced when I have 1 silver and 1 chloride. I have right now 3 chlorides and 1 silver on my reactant side, so I can tell it's not balanced. Moving on from there, I have my aluminum. I also have 3 nitrates. Here I only have 1 nitrate. So I'm going to have to find a way of putting enough nitrates on this side and putting enough silvers on this side in order to make what I need to over here. The complete reaction is going to have to reflect enough silvers to react with the chlorides and enough nitrates to end up with the aluminum. Right now I don't have that in my equation. What can I do to fix that? I can do 3 silvers, and since the ratio of silver to nitrate and silver nitrate is 1:1, I need 3 silvers and then I would need 3 nitrates. So now I have the number of nitrates I need. Now I have the number of silvers to interact with the number of chlorides. And the last thing was every silver finds a chloride, it becomes silver chloride. My reaction would therefore be 3 silver nitrates plus aluminum chloride will yield 3 silver chlorides and aluminum nitrate. I have aluminum, 3 nitrates, 3 chlorides, 3 silvers, everything's balanced. Now for my net ionic equation, again, I look at what changed. Aluminum did not change on either side. Nitrate did not change on either side. Silver chloride did. Silver chloride is now a precipitate. It was an aqueous dissolved solution, now it's a precipitate, which means my 3AgCl is part of my net ionic equation. What made the 3AgCl? It was 3 silver ions and 3 chloride ions. And my true net ionic equation, I'd divide each of these by 3. I would get 1 silver plus 1 chloride yields silver chloride. That is my net ionic equation. I hope that this makes a little bit more sense. Especially the balancing part is going to be essential for everything we do from this point forward.